Okay. Chapters 5 and 6, worksheet, YouTube video. Z-scores. Question 1. What information is provided by the sign plus minus of a z-score? What information is provided by the numerical value of the z-score? All right, so the answer is the sign of a z-score tells you whether the location is above or below the mean. Positive means you're above the mean. Negative means you're below the mean. And the magnitude, or the actual z-score, tells the distance from the mean in terms of number of standard deviation. All right. A distribution has a standard deviation of 6. Describe the location of each of the following z-scores in terms of position relative to the mean. All right, so the formula to solve this question is standard deviation times z equals position relative to the mean. So all you do here is, as you can see here, is you just plug in 6 and multiply it by each z-score given here. So 6 times 2 is 12 above the mean, right? Because it equals 12. So that means that that z-score falls, the score associated with that z-score is 12 points above the mean. And then you do the same for all the other ones. So 6 times 0.5 is 3 above the mean. 6 times negative 2 is 12 below the mean. And 6 times negative 0.5 is 3 below the mean. Next question. For a population with mu, or the mean of a population, that's all this symbol means. The symbol means the mean of a population. And this symbol means the standard deviation of a population. So for a population with mu equals 40 and standard deviation equals 7, find the z-scores for each of the following x values. So use the formula z equals x minus mu over standard deviation. This is the z-score formula. So all you do here is you plug in 40 for mu, 7 for standard deviation, and then you plug in all these x values for each question. So as you can see here, you just plug it in. So 45 minus 40 divided by 7, right? Comes out to 5 divided by 7, which is 0.71, etc. down, right? So it's 30 minus 40 equals negative 10 divided by 7 equals negative 1.43. All right, be careful and always recognize if it's a negative, and don't forget, right, it does change the score drastically, right? A negative 1.43 and a positive 1.43 are on opposite sides. So it does make a huge difference. So just look out for that and always be, cautious of forgetting to write in a negative sign when an answer is negative. And you just do that for all these other questions. Again, you're just plugging in each of these x values into the formula with the population mean and the standard deviation given. Okay, 7. A population has a mean of 40 and has a standard deviation of 8. For this population, find the z-score for each of the following values. So it's exactly like what we just did. So you're just going to use a mu of 40 and a standard deviation of 8 and plug in each of these x values, and you will get a z-score for each one. Remember, when you're rounding z-scores, always round to 2 decimal places. Because when you look on the table, all the z-scores are to 2 decimal places. So that is how we are going to round them in this class. Okay, for the same population, find the x value that corresponds to each of the following z-scores. So the formula to find x is z times standard deviation plus mu. Okay, so all you're going to do here is you're going to use this data, which is a mu of 40 and a standard deviation of 8, and the z-scores that are given in the questions, and you just plug them all into the formula. So for 0.75, it's just 0.75 times 8 plus 40, and then you get an x of 46. 0.25 times 8 plus 40, you get an x of 38, and so on and so on. All right, so just know when they're asking to find the x value, you can always use this formula, okay? As long as you have z, standard deviation, and mu, you could find x. Find the x value corresponding to z equals 0.25 for each of the following distributions. So the formula to use here again is z times standard deviation plus mu equals x. And you are just going to use the mu's and the standard deviations that are given, plug them in, and you do the same formula. 0.25 times 4 plus 40 equals 41. 0.25 times 8 plus 40 equals 42. 0.25 times 12 plus 40 equals 43. And 0.25 times 20 plus 40 equals 45. Okay, moving along. A score is 12 points above the mean, corresponds to a z-score of 3. What is the population standard deviation? Okay, so when we're given this information, when we're given how many points above or below the mean, the formula uses standard deviation equals points above or below the mean divided by z. So here we know it's 12 points above the mean, so we use 12. Now, if this was a negative, let's say it's 12 points below the mean, you would just use a negative 12. But here it's above the mean, so it's positive 12 divided by the z-score of 3. So we know that the standard deviation is 4. All right, for a population with a mean of 70, a score of x equals 62 corresponds to a z of negative 2. What is the population standard deviation? Okay, so when you're given mu, x, and z, you can easily find the standard deviation now by doing x minus mu divided by z. So you just plug in x, 62 minus 70 equals negative 8, divided by negative 2. A negative 8 divided by negative 2 equals 4. So the standard deviation is 4. Okay. In a distribution of x equals 64 corresponds to z equals 1, and x equals 67 corresponds to z equals 2. Find the mean and standard deviation for this distribution. Hint, no formula needed. Okay, so this is a conceptual question. All right, you don't need to use a formula to solve this. All right, if we know, we understand that a z of 1 means that it's 1 standard deviation above the mean, and a z of 2 means it's 2 standard deviations above the mean. So the distance between 1 standard deviation and 2 standard deviations, the difference between 1 and 2, z of 1 and z of 2, is the same distance between a z of 2 and 3, a z of 3 and 4, a z of negative 1 and negative 2, and so on. So we could just look at this so we know that the distance between a z of 1 and a z of 2 is 3, right? Because the value 64 corresponds to a z of 1, and the value 67 corresponds to a z of 2, right? So that distance is 3. And the mean, the mu equals a z of 0, right? Right in the middle of the distribution, right? So if a z of 1 is 64, and we know the distance between each standard deviation is 3, all you need to do is 64 minus 3, and you'll get 61, right? Because that will be the mu. And we know the standard deviation is 3, all right? So this is a conceptual question, sort of just understanding z-scores without having to do any real computations. All right, a distribution of exam scores has a mu of 80. If you score x equals 86, which standard deviation will give you a better grade? Standard deviation of 4 or a standard deviation of 8? So here you're going to do it twice using both standard deviations and see what z-score you get. So you could see here, you do 86 minus 80 divided by 4 equals a z of 1.5. And then you do 86 minus 80 divided by 8 equals 0.75. What is the larger z-score? What z-score is furthest from the mean on the positive side? Well, they're both on the positive side. 1.5 is bigger. So a standard deviation of 4 is the correct answer and will give you a better grade. B, if your score is x equals 74, which standard deviation would give you a better grade? A standard deviation of 4 or a standard deviation of 8? So again, we're just going to plug in 8 when we do the z-score formula. So 74 minus 80 divided by 8 gives us a negative 0.75. And we do 74 minus 80 divided by 4 is a negative 1.5. What's the larger z-score? Well, negative 0.75. Why? Because you're closer to the mean, right? A negative 1.5 is further away, right? You're going further to the left, so it's a worse score, right? A negative 0.75, you're starting to get closer to the 0 and to the positive side, so it's technically larger, right? Because it's closer to the middle, and the negative 1.5 is further away, so that's a worse grade, right? The further you go to the left on a z-score, the further you are away from the population mean in the negative sense, which means that it's a worse score. So in this case, the negative 0.75 is the correct answer. So that represents the standard deviation of 8. A distribution with a mu of 62 and a standard deviation of 8 is transformed into a standardized distribution with a mu of 100 and a standard deviation of 20. Find the new standardized score for each of the following values from the original population. Okay, so there's 2 steps here, right? So the formula to use is this 2-step formula. First, you find the z-scores of the distribution before it's transformed. Then you take that z and multiply it by the new standard deviation and the new mu. So as you could see here, for x equals 60, we do 60 minus 62, which is the original mean, divided by 8, which is the original standard deviation, equals a z of negative 0.25. Now we plug it into this formula, and we take that negative 0.25 times 20 plus 100, right? Because 20 is the new standard deviation and 100 is the new mean, right? And we are able to get the new standardized score, which is 95, okay? And again, you do that for each of these questions. Negative 1 times 20 plus 100 equals 80. 1.25 times 20 plus 100 equals 125. And negative 0.5 times 20 plus 100 equals 110. Okay, so that is how you transform z-scores to a standardized distribution using whatever mean and standard deviation you want to use. In this case, the question asks to use 120, right? Just to make the numbers simpler, right? It's easier to read a graph or present information when numbers are cleaner, so to speak, right? A mean of 100, right, is easy. Everybody could, see 100 and understand 100, and a distance of 20 for one standard deviation, is better to present than a mean of 62 and a standard deviation of 8. So we could transform that using this formula to make it cleaner and make it easier to present with research, or for presenting it to the media, or for presenting it in a report, etc. All right, so that's it for chapter 5. There's a lot of information, but this is all going to need to be used in chapter 6. So let's move on to chapter 6. So find each of the following probabilities for a normal distribution. All right, so you need to understand the greater than sign and the less than sign. And we're using the Z table in the back of the textbook. That's Appendix B, page 699 to 702. So the first question asks, what is the probability of z being greater than 0.25, right? So we locate 0.25, and remember, draw this out graphically. Where does 0.25 land, right? It lands to the right of the mean, right? Because it's positive. So now you're either going to look in the body or the tail, all right? That's going to be on the table, column B or column C. All right, so we're using column B and column C for this question. So you go to 0.25 on the z-score table, and you have to choose one. You have to choose whether it's going to be the body or the tail. Well, since the 0.25 is on the positive side and we're looking for greater than, we're going to use the tail, because the body and the tail equals the whole distribution. So in this case, the tail is going to tell us everything above 0.25. What is the proportion above 0.25? And that, if you go and look at the tail of 0.25, it is 0.4013. All right. Z is greater than negative 0.75. So if we go to negative 0.75, that's on the left side of the distribution, right? And we want to know everything greater than that. Well, think about it. If it's negative 0.75 and you want to know what's greater than it, then you're going to look in the body, because there is more above negative 0.75 than there is below negative 0.75, right? Above negative 0.75 is the body. All right, so whenever there's a negative and it's asking for greater than, you're looking in the body. And when there's a negative and they're asking for less than, you're looking in the tail. When there's a positive and they're looking for greater than, you're looking in the tail. And when there's a positive and they're asking for less than, you're looking in the body. So C, the probability of Z being less than 1.20. Well, 1.20 falls on the right, and we want to know everything, the probability of what's less than that. So we will look in the body. And D, what is less than negative 1.20? Well, negative 1.20 falls to the left of the distribution. So we will look at the tail to see everything under that, because to the right is a bigger portion of the distribution. So we are looking at the tail. And these are all the answers when you look at them in the z-score table. Okay. What proportion of a normal distribution is located between each of the following z-score boundaries? All right, so here they want to know the proportion that's between a negative 0.5 and a positive 0.5. So when you're looking for the distance in proportion between a negative z-score and a positive z-score, all you do is go to those z-scores and go to column D and add them. So in this case, right, they're the same numbers. So you're just going to add, and remember, it's a symmetrical distribution, so there are no negative z-scores on the table because everything is symmetrical, so the proportions will all be the same. So between negative 0.5 and positive 0.5, you just go to column D and you add column D twice, right, for both of them. So column D for a negative 0.5 plus column D for a positive 0.5. You do the same for negative 0.9 and positive 0.9, and the same for negative 1.5 and positive 1.5. All right, so now D is a little different, because now we want to look at the distance for a positive 1.25 and a positive 2.25. So here, what you do is you're still going to go to column D, but you're going to take the larger proportion, which is 0.4878, which is represented by the number 2.25 in column D, and you're going to subtract 0.3944, which is represented by a positive 1.25, right? Because we want to take away what's being added twice, right? Because if it's between mean and z for 2.25 and 1.25, right, there's going to be extra space there. So we're subtracting the smaller one out, and that will give us the exact distance between these two z-scores. All right, so for a rule of thumb, if they both fall on, because if these were both negative, you would do the same thing. You would take the larger probability and subtract it by the lower probability, or another way to say it is subtract the lower probability from the larger probability, or proportion, however you want to look at it. So that's the rule. So if the signs are opposite, you add column D. If the signs are the same, you are subtracting the smaller one from the larger one. Okay. Find the z-score location of a vertical line that separates a normal distribution as described in each of the following. So you're going to look up the proportions in the tail or the body, column C or column B. So 20% in the tail on the left, right? So what you do here is you're going to look in the column of the tail, right, which is column C, and you're going to look for the z-score that corresponds to 20%, right? So everything is in decimals on a z-score. So 20%, what's 20% in the decimal on a z-score table in the proportion section would be 0.2000, right? There's always 4 decimal points in the proportions of a z-score. And it's in the tail on the left, right? So if it's on the left, then if it's on the left of the distribution in the tail, we know that it's negative, right? So you're going to see that it corresponds to a z-score of 0.84, because you'll see 0.84 is the closest to 20%. And then what you have to do is understand that since it's on the left, it will be negative. So 40% in the tail on the right. So you're going to go look in the tail column, look for what z-score is closest to 0.4000, and you're going to choose either a positive or negative version. And since it's on the right, it will be a positive 0.25. All right. If it's negative, always put the negative sign. If it's positive, you could just leave it as the regular number because it's known that it's positive, or you could put the positive sign. Either one works. 75% in the body on the left. So in this case, 75% in the body on the left. So if 75% of the body's on the left, right, we know that that z-score must be positive, right? Because the z-score is split in half, 50%, 50%. So if 75% of the distribution is falling to the left, that means that that z-score must fall on the positive side. So you're going to look for so you're going to look at column B, right? Yes, column B for the body. And you are going to look for 0.7500. You're going to look for what z-score corresponds to that the closest. And that would be a z of 0.67. And we know it's positive because if the body is on the left, it must be on the positive side because it's taking up more space. So the only way, if a body is on the left, you know the z-score is definitely going to be a positive z-score. 99% in the body on the right. So again, you're going to go look for 99% in the body, right? So that would be 0.9900. What number is closest to that? And when you go look in the body section, you'll see the closest number to 0.9900 in the body is 2.33. So if 99% of the body is on the right, basically almost the whole distribution is on the right, you know that z-score must be starting on the left, right? So that's why it's a negative 2.33. Okay, find the z-score boundaries that separate a normal distribution as described in each of the following. So how we do this is we divide the percentage in half, find the column D z-score that is closest to that percentage, and write the answer in plus minus form. So for the middle 20%, we simply do 20 divided by 2, 10%. Now we look for the z-score that corresponds most closely to 10% in column D, which is the column that represents between the mean and the z. So you look for 10% because we're looking for half of it, and then the plus minus will give you the distance between both of those scores, which will give you the middle 20%, the two z-scores that represent the middle 20%. So in this case, if you go to a point, if you look at 0.25 on a z-score table, you'll see that in the body, in column D, it is closest to 10%. So it would be plus minus 0.25. Same thing with B. So the middle 50%, 50 divided by 2 is 25%. So you look at 0.2500, look for in column D, look for the z-score that corresponds closest to that, and just plus minus it. So plus minus 0.67. 95 divided by 2, you look for 95 divided by 2, you look for that proportion in the table, and you'll see that that comes out to plus minus 1.96. And for the middle 99%, you will see that the closest one are the same, right? So the 2.58 and 2.57 are the same distance. So in the answer key, 2.58 was what was on the answer key. It could also be 2.57, right? Because it's the same distance. So I'm really not going to be a stickler. If they're equal distance apart from each other, you could choose one or the other. But I'm going to keep questions like that off the test, so it's straightforward and no one gets confused. But for learning purposes, the best answer would be plus minus 2.575, right? Because in reality, this z-score table doesn't show everything, right? If we were running this in SPSS, you would get more exact numbers. So don't worry about getting a question like this where you could choose one or the other. Any question on your test will have only one answer. You won't be confused and have to choose two, but at least understand that since it falls directly between both of these z-scores, the best answer would be a z-score of 2.575, and that would put you exactly at the middle 99%. All right. So now we start with word problems using all the information we just learned previously in this lecture. So for a normal distribution with a mean of 80 and a standard deviation of 20, find the proportion of the population corresponding to each of the following scores. Scores greater than 85, right? So it's the same thing as when we did the questions when we were looking for the proportion greater than. Right? The only other thing we have to do here is we have to find the z-score first, right? In those questions, we were given a z-score. Now we just have to solve for z. So all you do here is you just plug in these numbers into the z-score. So you plug in 85 for x, you plug in 80 for mu, and 20 for standard deviation in the z-score formula, right? Z equals x minus mu over standard deviation. So 85 minus 80 divided by 20 equals 0.25, and everything greater than 0.25, right? Where are we going to look? If it's greater than a positive number, we're looking in a tail, 0.4013. So again, score is less than 100. You do 100 minus 80 divided by 20, which equals 1. So the z equals 1, and we don't want to know everything less than 1. So if it's less than a positive z-score, where do we look? The body. If you go to the body percentage, you'll see it's 0.8413. And you'll see a p is 0.5. P equals negative 0.5 here. And p equals... So the z equals negative 0.5 and positive 0.5, right? When you do 70... minus 80 divided by 20, you'll get negative 0.5. And when you do 90 minus 80 divided by 20, you'll get positive 0.5. Okay, so what's that? That is we want to know the scores, the distance between those two scores. And we know that when there are opposite signs, what do? You go to column D of both of those scores, which is negative 0.5 and positive 0.5, right? So it's going to be the same number, and you're going to add them. So you go to column D and add them, and you will get 0.3830. Okay. Don't be confused. I took this from a textbook, and it says m minus u over standard deviation. We're not taking sample means in this. That's for another lecture. So that should just be x minus mu, the formula we've been doing. So just disregard this. It's irrelevant information. I'm not sure why it's there. I took this from another source and just kind of edited it my own way and didn't realize it said M there. So don't get confused by that. The z-score formula that we're using for chapters 5 and 6 is z equals x minus mu over standard deviation. Okay, moving along. A normal distribution has a mu of 50 and a standard deviation of 12. For each of the following scores, indicate whether the tail is to the right or left of the score and find the proportion of the distribution located in the tail. All right, so again, they're giving us mu and they're giving us standard deviation. So what do? We just plug it in, right? So we do 53 minus 50 divided by 12. And that comes out to, that will give you a z-score. And then you just have to look. So whatever that z-score is, the numbers aren't on the answer key, but the z-score will correspond to the probability of 0.4013, right? And if the tail's to the right, we know that it's positive. All right, then you do the same thing for 44. So you plug 44 into the z-score formula. Well, if the tail is to the left, we know that that answer will come out negative when you plug it into this formula. And when you go to the corresponding tail, that corresponds to the z-score that you got from plugging in 44 minus 50 divided by 12. It will come out to 0.3085. And you do the same thing for 68. 68 minus 50 divided by 12, you get a z-score. And if the tail is to the right, you know it's a positive z-score. And the probability for that z-score is 0.0668. And then for D, you take 38 minus 50 divided by 12. All right, if the tail is to the left, right, we know that it has to be a negative z-score. So that answer will be a negative z-score, and the probability in the tail of that z-score is 0.1587. Okay. IQ test scores are standardized to produce normal distribution with a mean of 100 and a standard deviation of 15. Find the proportion of the population in each of the following categories. So genius or near genius, IQ greater than 140, right? So what do you do here, right? We're going to look for greater than 140. And just by looking at the number before even computing it, you know 140 is above the mean. So the z-score is going to be positive. So when you're looking for something above a positive z-score, right, we're always going to be looking in the tail. So you do 140 minus 100 divided by 15. You get 2.67. You go to the tail of 2.67 and you get this probability. Now, they want to know what's the proportion between an IQ of 120 and 140. Again, you're right away when you hear something like that, you know what you're going to do. Well, you're going to add column D's right there, right? Because we're looking between, but we're not adding because they're both on the same side. So if they're both on the same side, we take the larger proportion and subtract the smaller proportion from it, right? So if they were both on opposite sides, we add them. But since 120 and 140 are on the same side of the distribution, right? They're both on the positive. We know that just by looking at the numbers because 120 and 140 are above a mean of 100. So you just plug that in. So you plug 120 minus 100 divided by 15, you'll get 1.33. And you do 140 minus 100 divided by 15, and you'll get 2.67. All right, we're looking for the proportion between those two z-scores. So again, you take the probability of 2.67 in column D minus the probability in column D of a z-score of 1.33, and you will get 0.0880. And then average or normal intelligence, IQ between 90 and 109. Okay, so you know already 90 is below the mean of 100 and 109 is above the mean, and we're looking for between that. So right away, before you even solve anything, you know you should tell yourself, all right, I know what to do. We're going to add column D's for both of the z-scores that corresponds to these values. So now you just plug in the formula, 90 minus 100 divided by 15. You'll get a negative 0.67. And then 109 minus 100 divided by 15, you'll get a positive 0.6. You go to column D's for both of these numbers, you add them, and you get 0.4743. All right, number 8. The distribution of scores on the SAT is approximately normal with a mean of 100 and a standard deviation of with a mean of 500 and a standard deviation of 100. For the population of students who have taken the SAT, what proportion of SAT scores greater than 700? So what do we do here? We'll plug it into the z-score formula. 700 minus 500 divided by 100, right, equals 2, right? 200 divided by 100 equals 2. So we know the z-score is 2. Now, if we're looking for greater than a positive z-score, we always look in the tail. So you get a P of 0.0228. What proportion of SAT scores greater than 550? So you do 550 minus 500 divided by 100 equals a z of 0.5. Still a positive z-score, and we're looking greater than. So if we're looking greater than a positive number, well, a positive z-score, we look in the tail. If you look in the tail of 0.5, you will see that the proportion is 0.3085. All right, what is the minimum SAC score needed to be in the highest 10% of the population? Okay, so the highest, what is the minimum SAC score in the highest 10% of the population? All right, so here, right, we're not given that much information, so we have to go find that z-score. So what you do here is the highest 10%. Well, if we're looking at the highest 10%, where is that? That's going to be on the right and higher, right? So we're going to look in the tail. So we are going to look for the z-score that corresponds the most to 10% in the tail, 0.10000 in the tail. So you go and look in the tail column, and you look for the z-score that is closest to that 10% in the tail. So you go, and that number will correspond to 1.28. Go check it on your table. And now we are going to have to solve and get x. Well, remember the formula that we did earlier in the lecture? If you have a z and you have a standard deviation and you have a mean, you can get x. And the formula is written above, but I'll just say it. So x equals z times, so you're going to do negative 0.25 times 100, right? Negative 0.25 times 100 is what? It's negative 25 plus the mean plus the mean, sorry. So negative 0.25 times the standard deviation equals negative 25. So negative 25 plus 500, that equals 475. All right, so that is the score of, I'm sorry, I just went from C to D, and I've been doing this video for a while now, so I'm just going to backtrack. Okay, so the same formula it's the same formula, but we're going to do 1.28 times 100, which is what? 1.28 times 100 is 128, plus 500, right, plus the mean equals 628. So the minimum SAT score needed to be in the highest 10% is 628. My apologies for if anybody got confused there. All right. If the state only accepts students from the top 60%, what is the minimum SAT score needed to be accepted? So think about it. The top 60%, it's another way of thinking about the body to the right. So if the body is to the right, then you know that that z-score has to be negative, because if the body's to the right, it has to be a negative z-score. So we're going to look in the body, right? And we know it's the body because if it's the top 60%, right, is 60%, that's more, right? 60% is higher than the rest, which is 40%, right? Because the whole distribution equals 100%. So you're going to go and look in the body column and look for what number is closest to 60% in the body, which is 0.6000. We look for, in the body, the closest z-score to that number. And if you go, you'll see that that is a z-score of 0.25. But we know that that z-score must, the top 60%, right? The top 60% means that number is going to fall below the mean. So it's going to be a negative 0.25. And what I did in the previous question, I accidentally started solving this one. You simply take, to find the x value, the actual score that you needed to be accepted to be in the top 60%, you do z times standard deviation. So negative 0.25 times 100 is negative 25, plus the mu, which is 500. So negative 25 plus 500 equals 475. Okay. Information from the Department of Motor Vehicles indicates that the average age of licensed drivers is a mu of 45.7 with a standard deviation of 12.5. Assuming that the distribution of drivers' ages is approximately normal, what proportion of licensed drivers are older than 50 years old? Okay, so what do? You're going to plug in 50 for the x into the z-score. So if you do 50 minus 45.7 divided by 12.5, you will get 0.34, right? Or rounded to 0.34. Right? You're always rounding z-scores to 2 decimal places. Right? And so if we're looking for older than 50 years old and we have a positive z-score, if we're looking for above a positive z-score, where are we always looking? The tail. So if we look at the tail of a z of 0.34, the probability is 0.3669. All right. Last question. What proportion of licensed drivers are younger than 30 years old? All right, what's 30? 30 is below the mean, right? So we're looking for younger than that, so we're looking to more left of that. So we know that where we're going to look, we already know we're going to be looking in the tail. So you do 30 minus 45.7 divided by 12.5, you'll get a negative 1.26. And again, you have to decide whether you look in the body or the tail, but we're looking for everything that falls below negative 1.26, because 1.26 represents the z-score of being 30 years old. So everyone younger than 30 years old, what's the proportion of drivers younger than 30 years old? And that is a proportion of 0.1038.